This is lecture 29 on urban transportation planning. We are in the process of discussing the fourth important analytical step in the transportation planning process, namely route assignment. You may recall in the previous class we discussed about route choice behavior by travelers. We learnt about three principles of route assignment based on user equilibrium, system equilibrium and stochastic equilibrium. And finally, we understood that in most cases user equilibrium is the basis for traffic assignment in transportation system network. Once we decide on the method of assignment, then we are clear that the users will follow the minimum travel time path or the minimum path involving the generalized cost of transportation. This indirectly implies that we need to identify the minimum path from each of the zone centroid to all the other points of interest from that particular zone. So that is how we discussed about determination of minimum path from a given traffic zone, right. And in that connection only we discussed about the minimum path tree as well as the definition of the minimum path itself. The minimum path may be that route of travel which has a least accumulation of time, distance or other parameters as and when we consider. As I said, the other parameters could be travel cost, comfort, convenience and so on. The sequence of nodes which defines the links comprising the minimum path from a zone centroid to other points of interest, that is very important, to the other points of interest, the points to which this particular zone centroid is actually connected in a network is called the tree or the minimum path tree. The tree is determined by starting from the zone centroid and progressively selecting the shortest path to the other nodal points in the network. We start from the zone centroid and proceed along the shortest path. And we have considered this example to understand building of minimum path tree. The problem is build the minimum path tree from zone centroid 15 to all the other nodal points shown here. As you could see, this is not a complete transport system network, it is just a small segment of a road network linked to zone centroid 15, right. It is just to understand the principle of building minimum path tree. To distinguish between zone centroid other zones, you can see 15 is connected by dotted line and all other links are continuous lines, right. Let us see how to proceed further to build the minimum path tree. It is a simple principle of identifying the minimum path. We start from 15 and there are two connecting nodes to 15. The nodes are 12 and 16. The travel time to 12 in minutes is 3 minutes and travel time to 16 in minutes is just 1 minute, is not it. So that is how we are going to proceed. Starting from centroid 15, we go to each connecting node and note the time of travel to each node. Thus we can write travel time from 15 to 16 indicated here as T15-16 is equal to 1 and T15-12 is 3, is not it. And then the node closer to the centroid 15 in time is considered next. Why considered next? Why should we consider the node closer to the centroid first? Why not the node farther to the centroid first? Any response?
It's the shortest distance to have to be calculated, sir.
Yes, that is a logical reason. Anyway, we are interested in shortest path. Why first taking the node which is farther away? But it does not mean at the beginning itself that the farther node is not going to fall on the shorter path. Okay, we may not be able to say at this stage, but just some algorithm has to be followed to complete the process. Okay, it is just conventional to go to the next shortest node. It is not mandatory, in fact, right. From node 16, the cumulative time to travel from the centroid to another node directly connected to node 16 is then found. So 15 to 16, then proceed further from 16, and please perceive the network clearly. And so if you proceed from 16, 16 is connected to 13 and 17, 13 and 17. So but the path from 15 to 13 through 16 takes about 5 minutes. T 15-16-13 is 5 minutes, and T 15-16-17 is 3 minutes. The next closest node to centroid 15 is now taken, closest in terms of the cumulative travel time, right. Accordingly, we find that nodes 12 and 17 have the same travel time of 3 minutes, 12 and 17, right. And you may have to go back to see the travel time of 12. 15, 12 is also 3 minutes, right. And here we find 15, 16, 17 also has 3 minutes as travel time. So there is a tie. Even if you apply the norm of choosing the node which is the closer one to the starting node, we find there are 2 nodes with equal timings. So there should be some conventional algorithm to take care of this kind of situation. In such a case, the node with smaller number can be taken up first. It is only a suggestion, can be taken up first, smaller ending node number. We have in the previous case 12 as an ending node, here the ending node is 17. So obviously we can proceed from 12 to work with the algorithm. So we find out the cumulative travel time from 15 to 12 and then to 13. 12 is connected to 13 and it is 4 minutes, and T 15, 12, 10, because 12 is also connected to 10, and we have 7 minutes as the cumulative travel time. And it can be seen from the above that there are 2 possible routes to reach node 13. They are 15, 16, 13 and 15, 12, 13. So we can reach 13 by 2 alternative routes. Which route you will choose? 15, 16, 13 costs you 5 minutes of travel time, and 15, 12, 13 takes only 4 minutes of travel time, right. So you have to obviously take the shortest path. So 15, 12, 13 is the right path to reach 13 from zone centroid, not 15, 16 and 13. Clear? That means 16, 13 is not the link which is going to form the minimum path tree, isn't it? The later is shorter in time and hence chosen, and the former is discarded. later is 15, 12, 13 and former is 15, 16, 13. This process is repeated until all the nodes have been covered by shortest path, right. The minimum path tree thus developed will be as shown in the figure. This is the minimum path tree. You can see that a number of links have become redundant and hence removed from the minimum path tree. This is what we are looking for. When you assign traffic, you can assign using this network. The rest of the links are useless as far as this particular zone centroid is concerned, if you take minimum path tree as the basis for traffic assignment. So, extend this methodology to cover the whole of the network, clear. And please remember we are going to work with traffic assignment or route assignment using computer program, because the volume of data to be handled is huge and the number of nodes and links involved will be in thousands, right. In that case it is not possible for us to draw sketches like this and try to find out the cumulative travel time. Obviously we must work with some other methodology. What is the possible methodology? Any suggestion? How did we represent the road network for the purpose of analysis? Do you recollect the discussion about link array table, link array? We represented the whole of the road network using a matrix, right. Link array can be used to represent your network. Use the same link array to identify the minimum path tree also. That is how a program can work. Program cannot work with figures like this, right. So, we must know how link array tables can be made use of to identify minimum path trees, which is very simple. Only point to be remembered is the algorithm. Step by step we should remember the algorithm, then the rest of the calculations will be automatic. So, minimum path algorithm. The basic minimum path tree algorithm begins at the node of origin, obviously node of our interest, node of origin where from we start, and proceeds outward successively, eliminating links that clearly do not belong to any minimum path emanating from the origin. Clear? It is a very general statement. Even if you are not very clear about the statement, you will be able to understand better when we take up an example. Just at least have some vague understanding of what is stated here, right. We are just eliminating links that clearly do not belong to any minimum path emanating from the origin. Clear? The minimum path tree seeking procedure is as follows. The tree table that contains every minimum path emanating from the mode of origin is what we call as the minimum path tree seeking table, and step 1 is as follows. Initialize the path impedance of the tree table at 0 for the node of origin and a very large number for all other nodes. What do you mean by this? Initialize a path impedance. Path impedance is nothing but, in simple terms, travel time, right. So, we are talking about the travel time required to reach that particular node. that is what is mentioned here as path impedance of the tree table at 0 for the node of origin. Obviously for the node of origin path impedance can be taken as 0 because we are going to start from there, right, and a very large number for all other nodes. When we say very large number, normally it is taken as, to be on the very safe side, infinity. Okay. Take the travel impedance as simply infinity for all the other nodes and take the travel impedance as 0 for the node of your interest, which is the origin. This large number ensures that the first encountered actual path to a node will be chosen from the origin. Okay. We will see how it really works after taking an example. Step 2, enter into a list the links ij that emanate directly from any node I just added to the tree, right. I will repeat, enter into a list the links ij, starting node, ending node details, okay, I and j details that emanate directly from any node, right, I just added to the tree. Just added to the tree, I will just explain to you more clearly or in detail when we take up the numerical example, right. What you need to understand here is just we indicate the numbers of the starting and ending nodes for the concerned links with respect to the considered or the node of our interest. Step 3, for each node j included in the list, add the impedance of link ij to the tree table's current total impedance to node I. This quantity represents the total impedance to node j via node I. It simply represents or explains the process of proceeding further and then identifying the nearest node and considering that node as node I to proceed further. If this value is smaller than the current tree table entry for node j, the current total impedance to j with a new total impedance and enter node I as a node that immediately precedes j. I should repeat to make things little clear. If this value is smaller than the current tree table entry for node j can be accessed by different alternative routes. Let us say we have got some value already as a cumulative travel time for j, right, and we are again calculating the cumulative travel time by another route to the same point j. If this latest calculated value is smaller than the current or already calculated tree table entry for node j, replace the current total, obviously because it is smaller, impedance to j with the new total impedance and enter node I as the node that immediately precedes j. Okay. To proceed further, you just name that node as node I. This operation replaces the longer path to node j with the shorter one just discovered. If the new total impedance is greater than the current tree table entry, proceed to the next link in the list. And return to step 2 unless the list is empty, in which case the tree table contains the solution. Unless the list is exhausted, you have to continue the process. I hope all of you have some vague idea of the steps involved in the process. We will just take a numerical example and see how these steps can be followed one by one to get the minimum path tree. To make the job of understanding easier, we will consider the same link array table about which we had a discussion in the previous class. Find the minimum path tree emanating from node 1 for the network described by the following link array table. It is nothing but the table that we have already seen. There are 14 nodes in the network, and nodes 1, 2, 3, 4 and 5 are zone centroids, and other nodes are road intersections. Clear? To perceive this link array table better, I will just show you the picture also. This is the network that we are talking about. Nodes 1, 2, 3 and 4 as well as 5 are zone centroids. Other nodes are road intersections, and there are 2 dummy links for zone centroid 4, and all other centroids have only 1 dummy link. Please try to capture this picture to understand the subsequent discussion clearly. Right? Now, our starting node is node 1. So, we are trying to build minimum path tree for node 1, right, which is zone centroid 1. Okay. Let us again recapitulate step 1. We are initializing the path impedance of the tree table at 0 for the node of origin, which is node 1, and a very large number for all other nodes. This large number ensures that the first encountered actual path to a node will be chosen. Once you complete this first step, this will be the result. We have listed all the 14 nodes, right, and the impedance to node 1 is indicated as 0. The travel time to reach out to node 1 is given as 0. That means we are starting from node 1 itself, and the travel time to reach out to all the other nodes has been given simply as infinity, very large number. And we anticipate some steps like total impedance to node j in step 1, step 2, 3, 4, 5, 6 etc. That is why we have got a comprehensive table prepared for the purpose. Similarly, we are interested to know the node preceding j, so that the link connectivity is clearly known to us. So, that has to be entered for every step or every step of assigning your traffic, right. Next, enter into a list the links ij that emanate directly from any node I just added to the tree. In this case, we can treat I as node 1, is not it, and we are interested in ij, all the nodes connected to node 1. Which node is connected to node 1? Node 6, if you recall, okay, node 6 is directly connected to node 1, right. Then for each node j included in the list, we would have included node 6 in the list. Add the impedance of link ij, the corresponding travel time to reach 6 from 1 has to be entered there to the tree table's current total impedance to node I. This quantity represents the total impedance to node j via node I. As of now, I is 1, j is 6. Okay. So, that impedance we can easily enter in the corresponding cell of the table. If this value is smaller than the current tree table entry for node j, node j is 6. For 6 we have entered a value of infinity. Obviously, the first step it is going to be much less than the current value of infinity. replace the current total impedance to J with the new total impedance and enter node I as node that immediately precedes J. So, this is the result that we get on completion of the steps that we discussed. Stage 1 is completed. Now we are in stage 2, right. In stage 2, link Ij as starting node of I as 1, ending node is 6, okay, and compute new path impedance. We have computed 0 plus 5 is 5 minutes, and then compare to tree table stage n minus 1, the previous stage which was infinity. So, we say 5 minutes is less than infinity. So, we accept this travel time as 5 minutes, okay. 1 to 6 is 5 minutes, even though it is obvious. We take this step because this is a step to be followed for a large network, okay. Since our network very small, we feel that it is very elementary, but this procedure has to be followed to cover thousands of links and nodes, right. Then go to step 3. This operation replaces the longer path to mode J with the shorter one just discovered. Of course, this is not there in the first step itself because we have not come to that stage. If the new total impedance is greater than the current tree table entry, proceed to the next link in the list. Then step 4, return to step 2 unless the list is empty, in which case the tree table contains the solution. So, this is the result that we get on completion of step 2. Are you able to appreciate this point? Node J of our interest is node 6, right, and to reach out to this node from our node of interest, the cumulative travel time is 5 minutes, 1 to 6, and for this node the preceding node is 1, is not it. We have started from 1. So, node preceding J is 1, node J is 6, and travel time cumulative is 5, right. Clear? Okay, we will go to the next step. Now, have a look at the link array. We have to proceed from node 6, is not it. We have come from 1 to 6 and proceed further from 6 to other nodes. And please note 6 is connected to, apart from 1, the nodes 7, 9 and 10. Nodes 7, 9 and 10 are connected to 6, right. So, let us proceed towards these 3 nodes from 6 following the same algorithm. If you do so, your I becomes 6 now. We are proceeding from 6, right, whereas in the earlier iteration 6 was J, now it is I, right, and J nodes are 7, 9 and 10 as we identified, and the cumulative travel time from 1 to reach 7 through 6 is 5 plus 8, 13 minutes, and cumulative travel time to reach 9 from 1 through 6 is 5 plus 5, 10 minutes, and the cumulative travel time to reach 10 is 5 plus 4, 9 minutes. Then check whether these current values are less than the values that we have assigned or that we have obtained for these nodes in the previous iteration, and previously we have assigned the values of infinity only. So, we find that all these numbers are less than infinity. We accept these things as the cumulative shorter path from node 1, right. So, obviously, we will be proceeding further from these nodes, and of course, this is the result. We are updating this table to reflect the changes that we have made. Now, to reach out to 7, total impedance to node j is 7, 13 minutes, and for 9 10 minutes, for 10 9 minutes. The node preceding 7 is 6, preceding 10 is also 6, preceding 9 is also 6, and preceding 10 is also 6. Preceding nodes are also written down. These are necessary to finally get the minimum path. That is the idea of writing down the preceding nodes also, otherwise you will not be able to get the link connectivity. Clear? Now go back to the link array. We have to proceed from 7, 9 and 10. Look at the connectivities to these nodes. 7 is connected to 2, of course apart from 6 we have already seen, 6 to 7 we have come. The new connectivities are 7 to 2, 7 to 8 and 7 to 10. And if you take node 9, it is connected to 6, which is already known to us, we have already done. Then 9 is connected to 10 and 12, and node 10 apart from 6 is connected to 7, 9 as well as 11. Clear? So, we are going to proceed towards these nodes from each of the 3 identified nodes. All these 3 nodes will become I now, and we are going to proceed towards j. This is what we have seen. What we need to do is this. Now 7 to 2, right. To reach out to 7, the cumulative travel time is 13, we have already seen 13 plus the additional link time, link travel time is 2, so total time is 15, and this is less than the initial assigned value of infinity. So, we are accepting this as the cumulative travel time from 1 to this node. And 7 to 8, 13 plus 4, 17, this is also less than infinity, so we are accepting. Then 7 to 10, 13 plus 7, 20. Check whether we have reached out 10 with a lesser travel time. You can see that we have already reached out 10 with a travel time of 9 minutes. 1, 6, 10 is 9 minutes, whereas now we get a travel time of 20 minutes to reach 10. Obviously, it is more than the previously established value for this particular node, so we are rejecting. Clear? Then 9 to 10, 10 plus 3, 13 minutes, and 9 to, of course, it is greater than 9, so we are rejecting. Please remember, we are reaching node 10 within 9 minutes as per the earlier calculation. There is no need to accept this, we can reject. And 9 to 12 is 7 minutes, 10 plus 7, 17 is the cumulative travel time, and to reach out to 12, 17 as of now is the shortest time, so less than infinity, we accept it. And then 10 to 7, 9 plus 5, 14, 14 is greater than 13, we are able to reach node 7 within 13 minutes, so we are rejecting this path. And 10 to 9, 9 plus 3, 12, 12 is greater than 10, again we have to reject this, this is not lying in the shortest path. And 10 to 11, 9 plus 5, 14, to reach out to 11, 14 is the shortest time as of now, less than infinity, we are accepting. Okay. All the rejected links will not appear in your minimum path tree, that is the point to be understood. Is that clear? Now what are the links that we, or what are the nodes we have reached out now? Better go back and have a look. So, where from to proceed now? That we have to see what are the cases we have accepted. We have accepted this node as the next one, and this 8 is also accepted, 10 is rejected, right, and then 12 is accepted, and from 10 we accept 11. This implies when you proceed further, we have to proceed from 2 as well as 8, then from 12 and then from 11. So, there are 4 nodes where from we need to proceed further. The related question is, can we proceed further with 2? 2 is zone centroid, okay, that means we have reached the end point, right. 1 to 2 path is complete, there is no need to worry about the extension from 2, right, the point of interest is already reached. So, 2 need not be considered actually. So, we need to consider only 8, then 11 and then 12, is not it. So, these are the nodes where from we need to proceed further, clear. So, when you consider node 8, look at the connectivities. It is connected to 3, 7 we have already seen, right. It is only one connection we need to consider, 8 to 3 needs to be considered. Then 11, 11 to 4, 11 to 8 and 11 to 10, 11 10 connection we have considered. Then we will be interested in 11 4 and 11 5, yeah, as well as 11 13 and 11 14, these are the connecting nodes. Then if you consider 12, 5, 9 and then 13, clear. So, by looking at this link array you should be able to perceive the picture, that is the most important aspect, and then proceed further. So, from 8 we proceed to 3, the cumulative travel time already to 8 is 17, the 8 to 3 travel time is 4, the cumulative time is 21 to reach out to 4, it is less than infinity. So, we are accepting. Also please remember 4, this node 3 is another zone centroid, we are reaching the end point of interest in this particular case, right. And then 11 to 4, 14 plus 4, 18, and to reach out to 4 this happens to be the least travel time as of now, 18 is less than infinity, we are accepting. Then 11 to 8, 14 plus 5, 19, but 19 is more than 17, because we have shown earlier that we can reach 8 with the cumulative travel time of 17, is not it. It is here, we can reach out to 8 with a cumulative time of 17 minutes. So, we reject it. Then 11 to 13, 14 plus 8, 22, 22 is less than infinity. So, we accept it, and then to reach 14 from 11, 14 plus 5, 19, 19 is less than infinity, we accept, and then to reach 5 from 11, 17 plus 2, 19, less than infinity, we are accepting. These are all new paths. And 12 to 5 is what we saw, is 17 plus 2, 19, less than infinity, we accept, and then 12 to 13 17 plus 6 23 we are rejecting. Why? Please, it is an interesting case. What we have given as title for this column is this: compared to tree table stage n minus 1. N minus 1 is stage 4 actually, right. Normally we compare to reject the values obtained in the previous step, whereas in this case it is very interesting to note that within this step we have reached out to this node 13 and got a value less than this value. That is why I have not written anything in this column, I have just written reject here itself, because it is not as per the guideline given on top of this particular column, isn't it? It is in comparison with the previous step, whereas what we do here is in comparison within this step. Anyway we have to reject, so I write reject here and reject in the final decision making column also, right. So where do we stand now? So this is the end point, there is no need to proceed further from 3, and what are the things we have accepted? There is scope to proceed further from 4 because we have accepted, and there is no way to proceed further from 8, and we can proceed further from 13 because we have accepted, and we can also proceed further from 14, and we can also proceed from 5, but there is no way to proceed from 13 here. Of course here there is scope. So the nodes where from we will proceed further are excellent, that is the point you have to make. I am happy that all of you are alert, right. So 3, 4 and 5 are zone centroids, there is no need to proceed further. So the nodes where from we need to proceed further are only 13 and 14, only 2 nodes, right. Of course this is the finished table to reflect the current situation. We are simply listing J and the corresponding total impedance and the node preceding J. This is just to help us to understand where we are with respect to cumulative travel time and the minimum path tree. Now we are proceeding from we decided to proceed from these nodes, and we find those nodes are n nodes, so there is no way to proceed further, isn't it. So our remark is this: all the links emanating from nodes 3, 4, 5, 13 and 14 are rejected, the list is now empty and the procedure ends. Clear? So we accept whatever we have done so far, and so this is the final value as per the tabulation we have initially made. We have got information about the cumulative travel time as well as the connecting nodes, and this is the final summary of the results that we have got. Okay, total impedance to J and node preceding J, that is what we want, and using this information you can make a minimum path tree. Before that, have a look at the network that we have initially considered, and the minimum path tree is this, from node 1 to all the other nodes. How many links are involved here? Thirteen links are involved, and the original network has how many links, including the dummy links? How many? Because dummy links are also shown here as minimum paths, even though they are not distinctly shown in dotted line. All the dummy links are included except one. We had 13 plus 6 19 links in the original network. If you can just look at, we have 13 links in the road network and 6 dummy links. So, totally 19 links, and 19 links have become just how many? 13. So, 6 links are not needed to reach out to all the nodes of interest from node 1, right. So, this is the minimum path tree. So, we will be assigning traffic from 1 to all the other points of interest following this route only as per user equilibrium assignment methodology. Is that clear? So, please understand that link array can be given as input to get minimum path tree from any node of your interest. That is a point to be understood very clearly. So, your input is just the link array, and you can click a button indicating your reference node. You will get this minimum path tree not in the form of picture, again in the form of a table indicating the cumulative travel time and the corresponding nodes. Clear? Now, let us discuss about the route assignment techniques. Even under user equilibrium principle, there are different techniques available for assigning traffic, right. The first one is all or nothing assignment technique. Second, multi-path assignment technique. Third, capacity restrained assignment technique. Basically, there are 3 possibilities for assigning traffic. Let us first discuss about all or nothing assignment technique. This technique allocates the entire volume of traffic interchanging between pairs of zones to the minimum path calculated on the basis of free flow link impedances, right. That is why this is called all or nothing assignment technique. You assign the whole of the traffic to a set of links or nothing to a given path. Okay. So, this as per this technique, the allocation is done to the entire volume of traffic interchanging between pairs of zones to the minimum path calculated on the basis of free flow link impedances. As I indicated to you, it is free flow link impedance that is taken as the basis for assigning traffic after identification of the minimum path tree. All the travel times that we indicated as link attributes are free flow travel times. After all interchange volumes are assigned, the flow on a particular link is computed by summing up all the interzonal flows that happen to include that link on their minimum paths. It is a very simple methodology. Let us take this a small example. Assign the following interzonal vehicular trips emanating from zone 1 to the network of the previous example. We have already built a minimum path tree. We will use the same tree and assign the traffic volume shown here from 1 to all other nodes of our interest. Okay. 1 is also zone centroid. We are going to assign the traffic from 1 to other zones 2, 3, 4 and 5. The traffic volumes are 1 to 2 is 800, 1 to 3 500, 1 to 4 600, 1 to 5 200. Normally traffic volume is quantified in terms of PCU, passenger car unit. You may recall we discussed about conversion of person trips into vehicular trips, that is one stage. Under heterogeneous traffic conditions, that too highly heterogeneous traffic conditions prevailing in our country, we cannot just measure vehicular traffic in terms of number of vehicles, even though it may be approximately okay under highly homogeneous traffic conditions where around 90% of vehicles are cars. And to have a realistic idea about traffic volume, it is very important to convert the heterogeneous traffic, different types of vehicles, into equivalent passenger cars, right. So these numbers indicate PCU values, otherwise you will not be able to check whether the capacity of a link is reached or not. That can be assessed only based on the traffic measured in terms of PCU, right. So I have just shown the result to you. You may recall the volume of traffic to be assigned from 1 to 2 is how much? 800 PCU. PCU per day or per hour, what is a normal measure? Per day, are you sure? It is per hour. Okay. We talked about assigning for morning peak, evening peak, non-peak hours and so on, it is hourly volume of traffic. We should change over from daily traffic volume to hourly traffic volume when we do route assignment. Okay. So you can see 800 PCU is loading this link, that is what I have written here. 800 is loading link 67 also, and 72 is also loaded with 800 PCU. That completes the traffic flow from 1 to 2, right, and 1 to 3 500 PCU. That 500 also loads this link. 16 is loaded with 500, 67 also is loaded with 500 because it is lying on the shortest path, 78 is loaded with 500 and 83 500, and 1 to 4 600 PCU, and 16 is loaded with that amount of traffic volume also 600, then 610 600, 1011 600, 11 600, and 1 to 5 200 PCU per hour. So 1 to 6 200, 6 to 9 200, 9 to 12 200, 12 to 5 200. Now sum up the assigned units of traffic volume for each of the links. We have 4 components for 16 totaling to 2100 PCU per hour, and there are 2 components for 67 amounting to 1300. All other links have only 1 component. Okay. Now the picture with regard to link volumes are very clear to us. So this is how we assign traffic as per all or nothing assignment technique. We have assigned all the traffic along the shortest path, that is why the minimum path tree is used. We assign nothing to the other alternative paths to reach out to these nodes from 1. Okay. That is how we just name this technique as all or nothing assignment technique. So we will stop here. To summarize what we have seen today, you may recall we started our discussion with understanding the procedure for building minimum path tree, right. We took a small numerical example and understood the basic principle involved in development of minimum path tree, and that was just for the purpose of understanding the principle. In reality, we need to make use of link array table for development of minimum path tree, and we went through the 4 important steps related to use of link array for developing minimum path tree, and we completed the process and understood how computationally the development of minimum path tree can be managed using link array table. Then we discussed about the 3 techniques available for route assignment, namely all or nothing assignment technique, multipath assignment technique, and capacity restrained assignment technique. We took a numerical example to understand better the all or nothing assignment technique. We will proceed the rest of it in the next class.